Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 25, 2026, just yesterday. It introduces a mathematically principled, training-free method to detect hallucinations in large language models, achieving about a 24% improvement in accuracy over traditional baselines. The paper is titled, Spilled Energy in Large Language Models. And as we'll see later, the fact that this works without any additional training overhead makes the results really promising for real-world use. So, Figure 1 illustrates the core advantage of this approach using two examples, a geography question at the top and a reasoning problem at the bottom. In the top case, the model incorrectly suggests Sydney is the capital of Italy. The Logit panel on the left remains green, showing the model is dangerously confident in this error. However, the spilled panel on the right correctly flags the mistake in red. Similarly, for the math problem below, the metric clearly separates the correct answer, 120, from the hallucinated value of 470, which standard confidence scores miss. While moving on to Figure 2, we see the mechanism behind these results. Panels A and B on the left illustrate the theory. The authors reinterpret the LLM as a sequence of energy-based models. Ideally, energy values between steps should match, but the contour plots show they often diverge, creating spilled energy. Panel C on the top right confirms this on math tasks, where correct answers in green cluster away from errors. Finally, Panel D at the bottom shows this separation holds across 9 datasets, enabling robust, training-free detection. Alright, well Figure 2 established the theoretical mechanism. Figure 4 tests its robustness across different domains. Panel A on the left charts the performance of probing classifiers, which are explicitly trained to find errors. You see a clear diagonal of high performance in red, meaning they work well on their training data, but they fail to generalize, shown by the blue off-diagonal areas. Panel B on the right plots how much spilled energy improves upon this baseline. The consistent red coloring indicates that the training-free approach yields superior results, essentially solving the generalization problem that limits supervised methods. Okay, while the previous figure highlighted generalization, Figure 3 drills down into the precision of error detection on math tasks. The top row displays results for Llama 3 and the bottom row for QN3. In the histograms across the first 3 columns, we see a clean separation, correct answers in green cluster at low energy values, while incorrect ones in red shift to the right. This distinction holds even for the hard cases in the third column, where errors are very subtle. Finally, the ROC curves on the right confirm that spilled energy, plotted in green, consistently achieves higher accuracy than the pink Logit baselines. So, while the previous figures visualize the concept, Table 1 provides the hard numbers across all 9 benchmarks and 4 model architectures. The rows group different methods, comparing the author's spilled energy approach against baselines like raw Logits and the probing classifiers from Orgad et al. If you look at the average column on the far right, the proposed method specifically utilizing min pooling consistently leads the pack. For instance, on Llama Instruct, it achieves an AUROC of roughly 73%, a solid jump over the probing baseline's 64%. This pattern holds true for Mistral models as well, confirming the energy metric reliably detects hallucinations without task-specific training. Well, Table 1 showed the overall performance, but Table 2 here breaks down a critical factor, the exact answer strategy. The authors found that narrowing the analysis to just the specific answer tokens makes a huge difference. Look at the exact answer increase column on the right. For the standard Logit baseline at the top, focusing on the answer only helps by about 9 points. But for the spilled energy method at the bottom, the gain is massive, over 24 points. This pushes the final accuracy to roughly 73%, showing that the energy spill is most concentrated exactly where the factual claim is made. Wrapping up, 2 takeaways stand out. First, we can detect hallucinations effectively just by tracking energy discrepancies during decoding, without any extra training. Second, this approach generalizes far better than supervised classifiers, offering a scalable path toward more reliable AI. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.